Hey everybody, I'm Max, and this is a passion project of mine called Open Quantum. And the goal here was to build a low-cost, accessible, hands-on demonstration of quantum experiments for students, educators, indie makers. But first, a little preview. So here are three of the most cutting-edge devices being deployed in industry. On the left is a quantum computer, in the middle is a satellite, and on the right is a portable brain imaging device. And what do these three devices have in common? Well, they all exploit intrinsic properties of individual atoms to give you novel capabilities that really haven't been possible until the last decade or so. And what they're leveraging is our understanding of atomic physics to implement what is being known as quantum engineering. So to start, what is atomic physics? So you might think atoms, the nucleus and electrons, so it's probably something related to nuclear physics. It is not nuclear physics, very different fields. Atomic physics is the study of individual atomic systems. And we started thinking about this roughly around the same time as the birth of quantum mechanics. And as such, for 50 years, it was more or less a theoretical field because we would think about individual atomic systems, but we couldn't really control these in nature. Atoms move around at about 1,000 miles per hour at room temperature and pressure, so you can't really stick them under a microscope. They're hard to study. But then in 1987 at Bell Labs, a team invented the magneto-optical trap. It looks something like this, and I'll get more into how that works in a bit, but what it allows you to do is isolate and control individual atoms so that we can start playing with them, not just on paper, but really in the lab with our hands, and understand what we can do with them. And so quantum engineering is something built on top of this, not just in atomic physics, but really anything that involves manipulating individual quanta of the universe. So these are, we know from quantum mechanics that a lot of things in the universe are quantized, like electron spin. Popular in industry are flux qubits, like what IBM is building their quantum computer out of, photon states, and atoms are no exception. Atoms have quantized energy states, so they're discrete, and there is some specific energy that separates them. And atoms move between these states by absorbing and emitting energy, commonly in the form of light. So some of you may have seen a hydrogen lamp, and the color is red because red is one of the dominant spectral lines of hydrogen. And that's the energy difference from its ground state to some excited state. When it decays back to the ground state, it emits this red color. So if you can control light, you can control atoms because the way they transition between these states is by these discrete packets of energy. But how do we do this practically? So we have a pretty good understanding of imprecise light-matter interactions where they're more stochastic, but we want to do it at will. We want to deterministically manipulate single atoms. So on the top right here, this is a neon sign. And what you do in a neon sign is you put high voltage across the tube, and you're ionizing some of the gas atoms, and then they collide with other gas atoms, they impart some energy, these atoms get excited, they decay back down, and they emit some light. So when you have a neon tube, neon is kind of a misnomer sometimes because it could be filled with other kinds of gas, and the type of gas determines the color of emission. But this is kind of a non-deterministic process. It's imprecise. So precise control we can do with lasers. So on the bottom right, here's a titanium sapphire laser. And what's happening here is that atoms are absorbing photons at a very specific energy, the energy difference from this ground state to some excited state. These absorbed photons are converted into kinetic energy, and then as they decay back to the lower energy state, through stimulated emission, they emit the energy difference as a photon, so you get more emissions. Laser is actually an acronym for light amplified by the stimulated emission of radiation. So now once we have controlled light, what can we do with it? Well, one of the simplest examples of this is radiation pressure. So light has momentum. This kind of is sometimes unintuitive because in classical mechanics, we learn that momentum is the product of mass and velocity. But actually, when you get to relativity, you find out that light has momentum because it has energy. And what that means is you can push things around with light by conservation of momentum. So this is how a solar sail works. Solar sail, you're taking photons emitted by a celestial object like stars, and the transfer of momentum as they bounce off is pushing this thing forward. But this is imprecise control because we don't control the emission of photons from stars. But we can control the emission of photons from lasers, and this gives us precise control of atomic motion. So I think one of the coolest and honestly simple examples of this, you can do this at home with a laser pointer and a Sharpie, as in this video. You can levitate individual particles. So right here, this is an example of an optical trap, and what this guy has done is he has trapped one of the ink molecules on the Sharpie, and it's hovering there in that trap. This is called optical tweezers. It actually won the Nobel Prize in 2018. And this goes beyond just being cool to look at. It's actually a very useful phenomenon. It's used a lot in bioimaging, so you can levitate fragile molecules to study them microscopically. But we can leverage it even further for quantum control. And to do that, first I need to go into the Doppler effect. So the Doppler effect you probably have heard of acoustically, like an ambulance going towards you, the wavefront is compressed, the frequency goes up, and then as it goes away from you, the opposite happens. The wavefront is stretched, the frequency goes down, and you hear the pitch shift downwards. But this actually applies to all waves. Waves in water, but also light. Light is no exception. So atoms moving towards a light source see those photons at a lower wavelength or a higher frequency. It's called blue shifting if you're familiar with astronomy. And photon energy is linearly dependent on the frequency, so that means the energy goes up. So that means if you're a photon with a reference frame energy below the transition energy of an atom, if the atom is going towards that photon, it shifts that energy up and it gets to the transition energy. We call this on resonance. So if we combine these two things, the radiation pressure and the Doppler effect, we can leverage a phenomenon called laser cooling. And so here on the chart, you see that the photon energy is different than the natural transition energy of the atom. But when they're going towards each other, the Doppler shift makes that energy the same. And the atom will absorb this photon. And since they're going in the same direction, it absorbs the momentum too. By conservation of momentum, you've bled off some of the momentum of the atom. And so if we do this with 3 counter-propagating pairs of beams, we can push these atoms to a central point. And this is the magneto-optical trap, the invention from Bell Labs. And there's a magnetic field component to this that requires a bit more quantum mechanics, but really what this does is it keeps these atoms stuck in the central point of this. And actually it's a bit hard to see, but in the middle of this glass cell, there's this floating point of fluorescence. And what that is about 100 million rubidium atoms stuck in the center of this trap. So you're cooling these atoms over and over. They're absorbing and then re-emitting light. And after a few million cooling cycles, almost all the kinetic energy has been bled off. So from those thousands of miles per hour at room temperature and pressure, the final temperature of the atomic ensemble is about 100 microkelvin, really a tiny fraction above absolute zero. So this is what it ends up looking like. This is a picture from an academic lab that I worked in by Min-Ho Kwon. I think one of the most beautiful scientific images I've ever seen. And up here, there's a thing that looks like a little fingerprint smudge, and what that is again 100 million strontium atoms at a collective temperature about 10 microkelvin. You can see this with your bare eyes because they're fluorescing. They're absorbing these photons and they're re-emitting them, and you can see this like floating light. And really, within that floating light, you can't see the atoms, but you know they're there. But so what? So this is a science experiment. How do we leverage this as makers and engineers? So one of the first applications of atomic physics were for atomic clocks. So if any of you worked in aerospace, almost every satellite has an atomic clock on board because they are far and above the most precise way to keep time. So the current definition of the second is kept by NIST, and it doesn't lose more than the second in 15 billion years. And the way this apparatus is constructed is by laser cooling. So they cool these atoms, and then they throw them up in a cavity, and as they descend back down, they put a microwave frequency through that. And the frequency that maximizes the excitation of these atoms is what you use to define the second. And there's the brain sensing helmet. So this is a company called Kernel. And what they have is an optically pumped magnetometer that sits next to your brain. So magnetic fields shift the transition energy of an atom. And if you know the frequency of the laser you're passing through it, then you can reverse engineer what magnetic fields your atoms are placed in. And from that, you can try to determine electrical signal in the brain. So as the magnetic field increases, fewer atoms will absorb photons because you're not on resonance anymore. And this allows you to do portable brain magnetometry based on atomic physics. And then probably the most popular application at the moment is in quantum computing. So atoms are cooled via this method, and then you individually levitate them in a large array like this. And these are optical tweezers. And another laser system excites items from this ground state into some excited state, and you encode that ground state just in terms of math as a 0, and the excited state is encoded as a logical 1. But because these are quantum objects, what you can do is you can put them in a superposition of the 0 state and the 1 state. You can entangle them by applying something like a Hadamard gate. And all of these transitions are carried out optically. And optical instruments, as far as instruments go, compared to electron beam instruments, ion instruments, like they're fairly simple. They don't require a lot of instrumentation. So this is one of the leading paradigms for quantum computing. And it sounds really expensive and complicated. And that was kind of my intuition, but then I started working in a lab where we're building these things, and the physics runs very deep, but I'm trying to build this open quantum project. And the goal here is that, well, I think understanding quantum mechanics shouldn't be limited to theory in classrooms, especially not only in higher education institutions. I'm not really good at sitting in lectures. Thank you all for sitting here and listening to me. I think hands-on experimentation is the best way to learn. It makes lessons tangible, it makes them memorable, it makes it more fun. So what I wanted to do is provide a low-cost and easy-to-replicate kit that would enable people to get into quantum science, whether that be independent makers or people like even in high school, getting them familiar with these concepts earlier and earlier, because otherwise they just become this inaccessible topic that is kind of synonymous with a really complicated topic. But what does this look like tangibly? So here's a picture of my kit. I actually brought it, and if you want to catch me after this talk, I'm happy to. You can touch it, you can manipulate it. We can talk about how it works. So there's a precision laser system. So this is an open source laser. It's all 3D printed. Again, PID controllers and phase locked loops, and more complicated optical phenomena like polarization, wave plates, photodetectors, digital signal processing. And then the third system of the apparatus is an ultra-high vacuum system. So you need an ultra-high vacuum system to, for instance, prevent collisions between ambient air molecules and the rubidium vapor you're trying to trap. Also, rubidium likes to oxidize, and also if it wasn't in a chamber, it would just float away. So this is actually quite tricky. You need about 10 to the negative 10 torr. But ultra-high vacuum is ubiquitous in science and a lot of engineering. And there are almost never courses, whether you're at an academic institution or on the internet, that would teach you how to set this up. So I think it's a really necessary educational resource for people to get into deeper, more technical areas of science, even if you're not interested specifically in atomic physics. Unfortunately, this is difficult to make financially accessible. It usually relies on precision machined stainless steel, and it, as of today, comprises the vast majority of the bill of materials of the apparatus. But it's something I'm hoping to make more accessible with some experiments in 3D printing and electroplating vacuum chambers, among other techniques for manufacturing and machining that would allow this to be distributed more widely. And even given the complexity and the cost of this, the bill of materials for me for this vacuum system is about $4,500 compared to the commercial offering for something that allows you to trap atomic vapor. It's about $25,000. And then the last component, which I think is maybe the most important, is that I want to provide an engineering first guide to optics, lasers, and vacuum science. Because again, I care about building things. I mean, I care about theory as well, but I think when you know how to build something, it becomes more tangible, it becomes more accessible. And so I want to provide a concise guide, because I don't like reading 400-page textbooks, to get people up to speed, how to put something together. Even if you're not trapping atoms, how do you put together a vacuum chamber? There's a lot of experiments you can do in a vacuum chamber. You want to understand the phenomena top-down, from what you can do with it, rather than from first principles, from bottom up. And the goal is to get people building as quickly as possible. And so here are some things that you might be able to do with the device. So you can make a Bose-Einstein condensate. This is one of the first applications of ultra-cold atomic gases. It's one of the most exotic states of matter, where everything is in a degenerate quantum state. This is more scientific. But then there are very engineering-oriented applications like accelerometry, gravitometry, cartography. So there's a lab at Berkeley that can map the subsurface, the topography underground with a magneto-optical trap. There's magnetometry, like the brain sensing, the brain imaging device, optical tweezers, so trapping atoms in specific configurations, making single photon sources if you're interested in, for instance, quantum key distribution, things like Raman scattering, quantum information experiments like executing Hadamard gates. There's really a huge spectrum of experiments you can run with this. And really, by my estimation, I think there are fewer than 1,000 of these apparatus in the world, because they're really limited to academic labs, national labs, well-funded quantum startups. So there are far more experiments that could be run than people and devices that are available to run them. So there's this really exciting landscape that can be explored even by someone with much less background, much less money. So the goal of the project is to drive down costs, increase engagement, and lower the barrier to entry for quantum physics. It shouldn't just be something you study in theory anymore, because we can provide tangible examples of this phenomenon. And again, to provide a development platform to explore all these exciting experiments, many of which are unexplored just because there isn't enough time on these apparatus in the world to run them. I want to keep all the parts 3D printed or available commercial off the shelf from convenient suppliers like Amazon and McMaster. I think probably a lot of you have seen open source projects that are brilliant, but they look impossible to replicate. And I want to avoid that. I want it to be as accessible as possible. You buy some things, you print some things, you stick them together, and it more or less works, modulo some alignment. And then the goal is to iteratively reduce the cost to below 5,000. I see that as the price point where, you know, it's no Voron, but maybe like a print NC in the reach of even an underfunded educational institution that wants to set up a hands-on teaching quantum lab. So if you're interested, you know, if you have some engineering skills and you're interested in seeing a practical demonstration of quantum phenomena, there's a lot of room for development on top of the platform. If you want to replicate it, there are a lot of components that you can use that I've developed. They're all on the internet. You can work with me. I do a lot of material science and optics. Please feel free to reach out. Send me an email. Here's my email for the project. And yeah, thank you all for coming. I want to shout out the Hacker Initiative. They gave me a grant, some little micro grants to fund this, as well as a unitary fund. And then I picked up a lot of this knowledge and skills at the Z Lab at Columbia, where I did my undergrad. But yeah, please find me after the talk. I have some devices here and would love to share more.